All right, so we've seen how delta G can be useful to tell us the spontaneity of a reaction and to tell us about how much work a reaction can do. So obviously delta G is important, so we want to know how to calculate delta G. So first we're going to start off with calculating the Gibbs free energy of a reaction and its standard state, right? So this little degree symbol again means standard state. And remember that means approximately, or it means 1 atmosphere of pressure. And then most of the time it means, 20, the heck is going on here? Means 25 degrees Celsius, right? So that's what we're talking about standard state, and solids and liquids are in their most stable state in these conditions. So from our previous reaction, we know delta G of reaction is equal to delta H of reaction minus T delta S of reaction. So we can see here that delta G is going to be a sum of these things, and so you know that the delta H of the reaction will be the delta H, or the H of the product, minus delta H of the reactants. And same thing here, you know that the delta S part will be the delta S in the products minus the delta S in the reactants, right? So where are you going to get these things? Well, you can find them in tabulated data sets. So you can just find the value in a table, and basically if they're reactants, make them negative. If they're products, leave them as they are, and mess with the stoichiometric coefficients to make sure everything is A-okay. So let's take a look at an example. Should be pretty simple. Same thing you did in Chem 101. Same thing we did with the entropy of a standard, or of a reaction in its standard state. So same type of thing here. So there's a tabulated data set. So maybe a reaction that you kind of want to take a look at is something like SO2 gas combining with half an oxygen of gas to get SO3 as a gas, right? And then you're told it's at 25 degrees Celsius. What's the delta G of the reaction? So from the above, we first know we have to find delta H and delta S and then plug them into the equation to get delta G. So let's take a look at the delta H of the reaction. And again, what you want to do is you want to flip the signs on the reactants because you're destroying them. These are kind of, you can think of this as, this is heat of formation, and then you can kind of think of this as entropy of formation. So you want to flip the sign for the reactants, not flip the sign for the products, multiply by the stoichiometric value. So our first thing we see is SO2. So we find SO2. Next up we have O2. We find O2 in our table. And then SO3, SO3. Obviously, this is super easy because the table contains exactly what we want, but that's not always going to be true. You're going to have to kind of find it for yourself. Cool. So we want to think about what values we want to multiply here. Since S is a reactant, we're going to multiply by a negative number. And since the coefficient is 1, we're going to just leave this as a 1. So we're going to multiply this number by negative 1. The O part, since it's a reactant, we're going to make it negative. And since the coefficient in front is 1/2, we're going to multiply by negative 1/2. This thing's a product, so we are indeed forming it. So we'll leave this as a positive sign. The coefficient in front of here is 1, so we're just going to multiply this number by 1. So all we have to do is find out what these numbers are and then sum them together to get our final answer, right? So sum. And then, so we have to find delta H and we have to find delta S here. So again, we're going to sum these, but the stuff that we're going to do, the multiples that we're going to multiply by are going to be the same for both. We just have to pull them from the table. So just be careful where you're pulling these table from, right? This is delta H. So you want to grab it up here from this delta H over here. This is delta S. So you want to grab the data from over here. So let's just go ahead and populate this data. This is -1 times SO2. Delta H is -296.8. kilojoules per mole. This delta H right here for oxygen is just going to be 0. So, I mean, it'll be plus, negative 1/2 times 0, which just ends up being 0, plus this SO3 times 1, which is this negative 295.7. And you can see all the units here are kilojoules per mole. And so we're all in kilojoules. So this will just be at the end kilojoules per mole. And then if you go ahead and do the math, you should get negative 98.9 kilojoules per mole. And now you're just going to repeat the same process for the entropy, right? So this will be negative 1 times this value right here, this 248.2, plus this negative 1/2. Right now, this value is not 0, right? So this is 205.2, plus this 1 times this 256.8. Add it up, do the math, you should get negative 94.0 joules per Kelvin mole, right? Make sure you pay attention to the units, right? The units here are joules per mole Kelvin or that kind of thing, right? The other thing you have to be careful here is this is in kilojoules, this is in joules. So again, you're going to have to kind of convert. We know our overall equation is delta G is equal to delta H minus T delta S of this reaction. And remember, in standard states, we generally assume 25 degrees Celsius. So we can kind of use this 25 degrees Celsius. The thing you have to do is convert it to Kelvin. So this number right here becomes this 25 plus 273. And so it ends up being 298 Kelvin. And then these other numbers, we go ahead and plug this one into delta H. Plug this one into delta S of the reaction, and then make sure you convert one of them. So convert, I don't know, this one to kilojoules per Kelvin mole, something like that, right? They've got to be converted. They've got to be in the same unit. So when you plug and chug, do that math, you should get negative 70.9 kilojoules. So what this tells you, this is negative right here. So this is spontaneous at standard states. At standard states. So this reaction is spontaneous at 25 degrees Celsius and assuming 1 atmosphere of each one of the gases. So that's one way you can find delta G from tabulated values, is when they give you this delta H of formation and this entropy, and then you can go ahead and tabulate them through and then use your final equation to solve. Another way is you can get the delta G of reaction from tabulated delta Gs. So this one's even easier. From tabulated, go with delta Gs. And these are delta Gs of formation again, so you want to think about forming them. If a reactant, you're going to be destroying them, so you're going to flip the sign by -1. So here's a tabulated data set. And then we can ask ourselves a question for a certain type of reaction, right? And again, this delta G of the reaction is equal to G of the products minus G of the reactants. So you're going to change the sign on the reactant. So let's take a look at CH4 plus 8O2 forming CO2 plus 2H2O. So a combustion reaction, combusting methane, if you're interested. All right, so what do? Well, we just basically take these values, sum them up, and get the right answer, right? Get our delta G of reaction. So you want to find them on the table and do what you need to do to them, right? So we can think about this first CH4, it's a reactant, its coefficient is 1, and so we're going to multiply this number by -1. This 8, or this 8O2, it's a reactant, so make it negative, 8 oxygens, 8 here. This time it's a product, the coefficient's 1, so we just multiply by 1. And then this time it's a product, the coefficient here, oops, my bad, messed that up. It should be a 4. Oops, my bad. I missed one part of the reaction. That's why it's looking wrong. Should be a 2. And then we also form 4 O3s. All right, so this is the delta G that we want to solve for. So at this last guy over here, it's a product, so we want to multiply by a positive 4, and we want to multiply this water by a positive 2. My bad about that. All right, so all we have to do is just find them in the table and plug in the numbers, right? So there's methane. We find methane right there. Here's O2. We find O2 right there. Here's CO2. We find CO2 right there. Here's water as a gas. So water as a gas. You got to be careful about that. Don't use the water as the liquid, right? The water is a gas here, so make sure you pull the value for it being a gas. And then O3, got to find O3 on the table. Bit of a trick question as it's not actually in the table. O3's value should be 163.2. So obviously in a problem you'd be given this value. And then you just kind of plug and chug to get the final answer, summing all of them at the end. So you have -1 times this -50.5 plus 8 times 0 plus 1 times -394.4 plus 2 times -228.6 plus 4 times 163.2. Sum all that up and you get a final numerical answer of -14 or -148.3 kilojoules, right? Think about the units here, kilojoules per mole. You can write kilojoules per mole. It's the delta G of the reaction, right? And so this negative right here means that it is spontaneous at standard state, so at 25 degrees Celsius. So again, even kind of simpler than last end, you just get the tabulated values, flip the sign for the reactants, multiply by the coefficients, add up the numbers. Super simple, super easy.